This is Finite Math, Chapter 5, Section 2, Compound Interest. Now remember from Section 1 that simple interest is interest that is paid only on the initial investment. Compound interest, on the other hand, pays interest on both the original investment and on previously earned interest. So our formula is going to be a little different for this. Our formula is A for amount earned equals P, still for principal, times the quantity of 1 plus I to the nth power. I represents the interest rate per compounding period. It's very important that you realize it's not just the interest, it's per compounding period. As we work problems, you'll see what we mean by that. And then N is the total number of compounding periods. We also have continuous compounding interest, and the formula for that is A equals P times E to the RT. Again, A is the amount of the investment at a given time. P stands for principal. E, it's the number E, the one that you find on your calculator. R stands for rate, and T stands for time. Okay, this is a Microsoft Excel spreadsheet, and the purpose of it is to give you an idea of the difference in the amount you earn on your investment when you have $1,000 and the interest rate is 10%. Column A shows you how many years have gone by. Column B shows you what you receive at the end of that year for compound interest, and column C, what you would receive at the end of that year for simple interest. And of course, the first year, there's really no difference. And initially, the difference isn't very much. There's only a $10 difference between the two columns in year 2. But you can see that by the time we get 20 years at the very bottom, you have more than doubled with the compound interest what you would have with the simple interest. Let's try an example using our compound interest formula. Suppose you have $1,000 and it's deposited for 6 years in an account that pays 8.31% per year compounded annually. You need to find the compound amount for A, that means the total amount after the 6 years, and then B, how much of that is interest. Pause the recording, try the problem, and resume the recording to check your answer. Here's our solution. Using our formula, P is 1,000, I is 0.0831 because it's being compounded annually. That means once a year. It's for 6 years, so once a year for 6 years, N is 6. Putting those numbers into our formula, we get $1,614.40. And then for part B, taking that amount and subtracting the initial investment of $1,000, we have $614.40. Here's another example. You have a $16,000 investment and you want it to grow to $50,000 within 18 years. What is the interest rate? And we're assuming annual compounding. Try this problem, pause the recording, and then resume the recording to check your answer. Again, we're going to use our compound interest formula. We know that our principal is $16,000 and we know we want to have $50,000, and we're going to have 18 compounding periods, once a year for 18 years. This time we're missing I, we're missing the interest. We're going to put all the numbers we have into our formula. We're going to use our algebra skills and solve for I. You can see the process there. And we discover that we have 0.06535 or 6.535%. This time we have $5,000 invested at an annual interest rate of 3.1%. And this time it's compounded continuously for 4 years. We want to find the compound amount. Give this problem a try, pause in order to do that, and then resume the recording when you're ready to check your answer. Using our continuous compounding formula, we're going to let P be 5,000, R be 0.031, and T is 4. And putting that in our calculator, again, please remember that E is not a variable, it is a number, it is found on your calculator. It is the natural base, if you remember from your algebra classes. Putting those numbers into our calculator, we get $5,660 Next, we have zero coupon bonds. With a zero coupon bond, the investor receives no money until the bond's maturity, when he receives both principal and interest. If you remember from section 1, generally speaking, a bond pays you interest every 6 months. This time, you don't get it every 6 months. Instead, you get it at the very end when the bond matures. Now, because you're getting it at the end instead of every 6 months, the interest is compounded semi-annually. That means twice a year. The purchase price of the bond is discounted from the face value. The face value of the bond reflects the principal plus interest. So whatever the face value of the bond is, you're going to be paying less than that for the bond itself. In this example, we have Doug, who bought a 15-year zero coupon bond. The interest was 4.5%, and he paid $12,824.50. What is the face value of the bond? Give this problem a try, pause the recording to do that, and then resume the recording to check your answer. So we're going to use our compound interest formula. We just talked about how this is compound now instead of simple. Interest is paid twice a year. So here's where remember we said that I is the interest rate per compounding period. It's 4.5% interest, so 0.045, but because it's compounded twice a year, we divide by 2. And the number of periods in 15 years will be 30, because it's every 6 months. So for I, we're going to do 0.045 divided by 2, and for n, we're going to use 30. Our principal, what he paid for it, is $12,824.50. Put all of those numbers into our formula, and we get $24,999.99618. Rounding up to the nearest cent, which we do when we're dealing with money, we find that the face value of the bond is $25,000. In this example, we're looking at inflation. The inflation rate is 3.5%, and we want to know how long it's going to take at this rate for the overall level of prices to double. Pause the recording, give the problem a try, and then resume recording to check your answer. Now, you may have wondered, what do I use for my principal and my final amount if what I'm looking for is time? I need some more numbers here. Well, the idea is we want to find the number of years it will take for, say, $1 worth of goods or services to cost $2. That's really the simplest way to look at it. So $1 will be our present value. Something costs $1 today. We want to know when that same item is going to cost $2 if the interest rate is 3.5% compounded annually. So we're going to put in 1 for P, we're going to put in 2 for A, 0.035 for our I. Since we're compounding annually, N, the number of times compounded, is actually going to be the same as the number of years because you're compounding once a year. So when you simplify that, you get 1.035 to the N equals 2. Now we need to figure out what N is, and there's a few ways to do this. Graphically, you can take your calculator, and for Y1, put in 1.035 to the X, and for Y2, put in 2, and figure out where the two things intersect. And I don't have the picture here. You can look at it on your calculator or in the text, but the X coordinate is 20.14879, so about 20.15 years if you do it graphically. Another way to do it, if you remember from algebra, to get a number or a variable out from a power, what you need to do is use logarithms. So if we take the natural logarithm of both sides, we can then bring the power out in front. So that gives us the n times the natural log of 1.035 equals the natural log of 2. Divide both sides by the natural log of 1.035, and we see that we get the exact same answers we got graphically. Now we're going to talk about the effective rate, which is also known as the annual percentage yield. This is the annual compounding rate that will produce the same amount of interest in 1 year as the nominal or stated rate with more frequent compounding. The formula for figuring this out is R sub E, that's effective rate, equals 1 plus R, which would be the stated rate, over M, the stated number of times compounded in 1 year, to the n power minus 1. We use the effective rate or the annual percentage yield for comparison purposes. When you have varying accounts that promise different compounding periods and different interest levels, finding out the annual percentage yield or the effective rate is a good way of comparing them and putting them on the same level. Okay, let's try this example. Find the annual percentage yield for a 5-year $100,000 CD at 1.73% interest compounded daily. Pause the recording to try this problem and resume the recording to check your answer. Okay, notice that in the process of solving the solution, they did a little bit differently, but if you look down about the third line here where it says subtract 1 from both sides, that is actually the formula we just talked about. It's 1 plus R over M, M being the number of times compounded, 365, to the 365th power minus 1. That's our formula right there. And when you use the numbers in that, you get 0.0175. So the annual percentage yield is about 1.75%. Okay, here's another example where we're going to find the annual percentage yield for two different accounts. So for A, we have a 3.35% account compounded monthly, and for B, a 2.33% account compounded daily. Pause this recording and find the APY for each of these situations, then resume the recording to check your answers. For part A, we see that when we put the numbers into the formula, our APY is 0.034019. So 3.4%, which is slightly more than the 3.35% that was the stated or nominal rate. For part B, putting the numbers into the formula, we get 0.023572, which is about 2.36%, which again is slightly higher than the stated rate of 2.33%. Let's look at another example. This time we're going to compare two banks. Bank A is lending money at 10% interest compounded annually. Bank B is offering 9.6% interest, but it's compounded monthly, and Bank C is 9.7% interest compounded quarterly. If you need to borrow money, at which bank will you pay the least interest? So what you need to do is you need to find the annual percentage yield, the effective rate for Bank A, B, and C, and you want to see which one is lowest. Pause the recording, try the problem, and resume the recording to check your answer. We find that Bank A, APY is 10%, same as the stated. Bank B is 10.034%, and Bank C is 10.059%. So Bank A actually has the better deal. The interest is, the APY is lower, and interestingly enough, the nominal rate is actually the highest there. What made the difference was the compounding. Now we're going to look at the present value formula for compound interest. Remember, the formula you had before was for the future value, for what you have at the end of the term. Now we're going to look at what do you need to put in now to have a certain amount in the future. So there's two ways of expressing it. P equals A over the quantity 1 plus I to the nth power, or if you prefer to use a negative exponent, you can do that and have A times the quantity 1 plus I to the negative nth power. Here we have another example. This time we have a zero coupon bond. Remember we talked about those earlier. The face value is $15,000. Remember, that is what it pays in the end. It has a 6% interest rate compounded semi-annually and will mature in 9 years. So what would be a fair price to pay for it today? In other words, what do you want the present value to be? Pause the recording, try the problem, and resume the recording to check your answer. All right, so putting these numbers into our formula, our future amount is $15,000, that goes on top. We have 1 plus 0.03. 0.03 is our interest rate. Why? I thought 6% was our interest rate. Well, 6% is our interest rate, but that's our annual interest rate. This is compounded semi-annually or every 6 months. So we have to actually do 0.06 divided by 2, and that gives us the 0.03. And we're raising that to the 18th power. Again, why? Well, it's being compounded twice a year for 9 years. 2 times 9 is 18. There are 18 compounding periods. When you put all of that into your calculator, you get $8,810.92. So you would expect to pay $8,810.92 and receive $15,000 from that in 9 years. Okay, here's another example. The annual inflation rate for the years 2010 to 2012 was 2.29%. The question is, how much did an item that sells for $1,000 in early 2013 cost 3 years before that? So $1,000 is going to be our future value, and we will need to find the present value, the value back in 2010. Pause the recording, give this a try, and resume the recording to check your answer. So again, putting our numbers into the formula, $1,000 is our future value. We have 1 plus 0.0229 to the third power. This is compounded annually, so we just use 0.0229, and we're talking 3 years in our time here. And we get $934.33. So an item that cost $1,000 in early 2013 would have been $934.33 in 2010. Actually, this is in your book. It's just a summary of the formulas that we've had in both sections, along with the variables that we use, the symbols in these formulas. So you might want to look this over, take note of it. Again, you do have a formula sheet. It is available on my website. You will be given that formula sheet for tests and quizzes. It is up to you to be familiar with how these formulas work. Hey, these are some classwork problems that you can try. I suggest that you pause the recording, attempt the problem, and then resume the recording to check your answers. Continue to do that until the end of the presentation. Pause the recording. Pause the recording. Pause the recording. And pause the recording.